All right. Hello, everyone. Welcome back. Thank you for being here on a rainy day. I appreciate that. And last week of classes before your final presentation for capstone. So all the things can make you not to be here. I'm going to give you an overview of this week, actually. And then we're going to start today's class. Faster. All right. So in light of all the craziness of finals, I'm canceling next Monday's class. So Friday is going to be last day of our class, which I will review the exam material. It won't be like the other two exams that I'll bring questions. I'll tell you what topics will show up. Most of you had interviews with me. Almost everyone, we have a couple left. So you know what kind of question I ask, plus everything after midterm 2. So you can bring cheat sheet exam 1, cheat sheet exam 2, create a cheat sheet of the rest of the material. But you're not gonna, for example, put a body plot with specific values in it, right? So that still counts as solutions. So you can have, for example, you can have the control law of a PID, control law of a lead and lag, but you cannot put any values in them, right? And based on my understanding, a lot of you need to study lead lag controller, pole placement, what they are, and how to use root locus. How did we create root locus? All right, since they are part of controller design and everything after midterm 2, they will be in your exam, even you learn about them before. Does that make sense? It's like in homework 5, I asked you about everything because this is the end of the class and you should have knowledge about that. I'm not letting you in. Yeah. When it's just what all right, so I changed the Wednesday's class a little bit, so I think these two will be enough to get you started on this data space. Yes, what's that? You can have a third cheat sheet, but I'm going to do the same thing. I'm going to walk around. If there is solution in it, I'm going to take it from you instead of just putting across, because this is like really important part. So you can literally bring the solution with you. I want you to be able to evaluate your understanding. Can you design a controller? For example, if I give you a hypothetical body plot and root locus, and I ask you how to fix the system, let's say I will give you also time response. Same thing that you did for your homework 5. That's part of your final, right? Can you do that? So be careful what you write. You can actually write it on Friday maybe, and then I can go and look to see if it looks okay or not. All right. And then Friday will be exam review. You would kind of know the kind of question if you just show up. You don't have to be here in person. Again, it's Friday, but you cannot be on Zoom. I will record though. I'll post a video, but if you're here, I can answer your question. If you're not, I can't. And Brett won't be here this week, I think. So he's not here today. It would be very difficult for me to check the Zoom for questions. So if you're on Zoom, if the point is just to be in class, be here. If just log in, I don't care. Friday is your option. You can be here or not, all right? And then we will have last class attendance. So there will be class participation. It will be more of an attendance. And I will ask you to fill out SEI there. So just take care of everything for this class. All right. Any question on how this week's is gonna go? No? Great. Now let's share lecture slide. I posted the lecture slide very late because today was crazy. So I'm sorry for that, but shouldn't be a problem, much of a problem. And I figured how to move my face. There. Stupid. All right. So we are going to finish this S domain and frequency domain and all the controller related to that. And we are going to take a peek into state space control. Same thing. No. So for state space control, do you remember the state space representation? We had the matrices and whatnot. Again, if we change the representation, it can help us to get other tools to design our controller. So if you wanted to design a PID controller, you can write the state space representation, go to MATLAB, convert it to transfer function, go from there. Or you could use the state space, go to Simulink, put a PID block, Simulink will connect and move between the two for you. But there are other controller that you can directly use a state space for. So we're going to talk about at least one of them this week. If we had enough time, we'll talk about LQR as well. If not, just pole placement. We have pole placement in state space as well. I brought a review of what the state space are to refresh your mind to go from transfer function to that. So we had two equations, right, for state space representation. One was the state equation, the other one was our output equation. Now, do you remember from going from a higher order differential equation, like second order, and going and writing state space? Then we had mass spring damper, we wrote the transfer function, we also wrote the state space, right? Now, we also, when we were there, discussed, hey, if this is a block diagram of a system, I can write differential equation from it, and I can write state space from that, okay? We're going to do that today to help you remind you what happened. But in the state equation, we have, so it is a linear combination between your states and your input, how it changed. Your x dot of t, or the rate of change of your states, is going to be equal to some A matrix times your state vector. Now, your state vector could be your position, velocity, pressure, temperature, whatever is the state of that system. That's and then if you remember, when we developed the A matrix represents the dynamic of your system, is the system itself. So x dot is A times X plus B times U, how the input is implemented to our system, right? This becomes our first equation, a state equation. Our second equation is our output equation, which depends on you as engineers, what you want to look at or measure, or if you have the ability to measure something in your system or not. Let's say you're trying to measure position, but you don't have an encoder. So you're not actually measuring the position. So measurement is literally a sensor, right? So the second one is your output equation. It could depend on your input. Most of the time, we assume for us that D matrix is 0, so there's no feed forward into our system that depends on our input. Usually your Y is Y equals C times X, and X your state variable. Basically that, hey, my output is equal a combination of my inputs, or let's say it's just based on position, based on velocity, or combination of both of them. So you can measure both of them, right? You decide what you want to look at, or if you can measure. You look at your system, I have a temperature sensor. I can actually read the output. You put that in your Y equation, all right? So we went through this, is just a reminder, so you don't have to go back and find that lecture. We always, when we use this method, we are making our equation simpler, going from differential equation to first order, so higher order to first order, and the second one is algebraic. Y is equal to CX, right? Now, previously, and also in your exam, I think it was exam 1, right? If you have a block diagram, you can write the differential equation from it. If you have a flow diagram, you also can write differential equation from it. All you have to do is to figure out where the state of your system are, where the states are. Let's say x, x dot, x1, x dot 1, x2, x dot 2. And once you have that, find the relationship between the state and the output and write those differential equations. Now, as a reminder, I want everyone to write differential equation for the system. Then from that, find your ABCD matrix, the state space representation. If this is just a reminder, so if I want you to start this so the rest of the lecture would make sense to you. All right, so I know it's been a while, so I'm going to give you a little bit of time. By the way, these two are the same system. I just represent both of them here. Now, you all know what is this guy? This is an integrator, right? So for integrator, you remember, if you have x1 here, what was integrated that became x1? X dot 1. So this side is x dot 1, this side of the signal, right? So go about that, use that, and then write the differential equation for this system and state space representation. So differential equations or equation, I don't know, you need to figure that out on your own. Or you can talk to your neighbor, try to do that. So to write the differential equation, your goal, so you're going to write the state space representation, right? So your goal is to find what x dot 1 is, what x dot 2 is. Because from there, you can write your state space representation. So this is what we're trying to write, define. But first you have to write the differential equation. All right, so this is kind of like signal and system kind of question. So if you haven't done it, just look at what I'm doing and be able to follow. Yes, everyone, look at the board. Adrian. So let's just start from x dot 1. So let's identify where it is located. So your x dot 1 is here, right? So we want to know how to create x dot 1. There is a u going inside that block, right? Summation. There's also x1 multiplied by 2 going with a negative sign. So negative 2 x1 of t, I'm not going to write t, plus u of t. Right? Now, x dot 2, let's go find that. This is x2, so this must be x dot 2 because we have an integrator. So this is x1 times d, so this is dx1, right? We have x2 times 3 negative, so this is, well, I'm going to write 3x2 and then I'm going to multiply that. So x dot 2 is negative 3x2 plus dx1. They're all function of t. I did not write that. So those are our differential equation. Now to write the state space representation, we want to make sure they're organized, and then we create A and B matrix. So our x dot is x dot 1, x dot 2, right? So this is your x dot. We need an A matrix. What's the dimension of our A matrix? 2 by 2, because we have two states, right? Now, all we have to do is fill in the blank. Well, we still have also B times U, UT. Now, let's fill in the blank from here. X dot 1 has negative 2 times x1, so negative 2. There's no x2, 0, and there is 1 U of t. Next line, I'm here, x dot 2 is negative 3x2, so this is negative 3, plus dx1, and there's no 0, no u of t, so that's 0. Then so this was our state equation. For state space representation, if you are asked about representation, you need to also write the output equation, right? Now, if we look at this system, here your y is equal to x2. Right? There is no line going from x1 to it. So this just means that y was chosen to be x2. So if I'm gonna write it with a different color, blue. So y is x2. We have C matrix times still x1 and x2 are our states, right? Same state. The only thing is we are only looking at x2, so this is 0, this is 1. Now, these two together are our state space representation. So, as you can see, C matrix only depends on the output measurement or what you are reading on the output, right? Which are combination of your states. It's never outside of that. And your A matrix tells you everything about your system. Now, if I wanted to find the poles of the system, what should I do? Yeah. So, which is, you find the determinant and then see what it is, right? You find that. So that's the pole of your system. If you want to see the system is stable or not stable, is there any pole that's on the right-hand side? The system is unstable. All right. Now, for designing controller in state space, you need to know this representation. So you have your system. The second things you need to know is that if this system is controllable, and to put the sensors in the system and to write the output, you want to know if the system is observable. Now, you will hear these two terms a lot. We are going to work with controllable first, and then we go to observable. Now, for pole placement method, we want to make sure our system is fully controllable so we can easily just place a pole wherever we want it. When we were in S domain using root locus, we had to make sure we choose a pole of open loop system that is under root locus. In this method, you can arbitrarily pick any pole. You don't have to think about if it's going to be on root locus or not. because we're looking at the closed loop system here. So it gives us more freedom. You can literally choose any pole. You just have to make sure first it is controllable. Then you write your control law. So to be controllable, we are going to, well, first the definition. The system is completely controllable if you can find a U that can transfer any initial state to a final state in time t. So if you're running your system, your simulation in t seconds, any of your initial states have to go to their final state between that time. You might ask, well, is there a possibility that's not? Yes. In some cases, you won't be able to predict or estimate what your state is going to be after a specific time. You want to check and see what are the requirements. So making sure a system is controllable, then control it. Now, to make our life easy, we're going to come up, we're going to write some definition based on ABCD matrix, because that's all we know about our system. And then we can check those. If your system is x dot equal to AX plus BU for controllability, you're going to look at the state equation. Is everybody listening? This is important. So for controllability, you're going to look at the state equation, which is this guy. Then you are going to create or form PC, controllability matrix. This is going to be your B matrix, then A times B matrix, A square B matrix until AN minus 1B. So you find your A matrix n by n, you find your B matrix n by 1, then you form your PC. Okay. If the determinant of your PC is not 0, then system is controllable. You also will hear rank of the system. It has to be n. So system is full. Now in MATLAB, you can find the rank of the system, basically rank of that. But when you are checking it yourself, you have access to MATLAB, you can find the determinant and see if it is non-zero. All right. Here's an example for you. Is the previous system. How cool is that? So you have ABCD matrix. You can just put it on previous slide. You forgot your A was -2, 0, D, and 3, -3, and your B was 1 and 0. So find what your PC is, then check the determinant of that. Hence, you have to bring the equation for the determinant with you for final exam. Hopefully, it exists still on your first exam. You don't have to write this data space representation. All you need is matrix A and B, which we did it in the previous slide. So We need to create PC, find it, find it. No, why? You don't like me? You don't know how to find the determinant? Go to the preferences slide. Are you taking notes? I was writing. Here, I'll go to the preferences slide. If you didn't take notes. That's why I said it's important. You need to have it. Can you tell if it's going to be controlled or not? Based on their value? Trying to figure that out. It is n. No, we will just get system. Means that you're not gonna get you, and I don't know, and you can have two things inside, but it's not just gonna be one. Because you could get you prime, you something, they're all different. Small p per launch output is different from how many you have inside. If you had, this is single input, single output, single input, but you could have p prime, u prime, that would be two input. No, u is the value. Like force, one, yeah. All right. Depending on like your system, you can be different things, but it's one value. All right. So things that we need to create based on here, we need B, we need AB, and since our N is 2, we only need AB, right? So AB is going to be -2, 0, D -3 times 1, 0. So you should be able to do this by hand. -2, D. Now, PC is AB, then place the other one. Determinant of PC is going to be D. Since D is constant, because it says here constant, and by constant, let's remain non-zero. The system is controllable. Meaning that we have enough information about both of the states, X1 and X2, that we can control both of them. So that will be completely controllable. And that's because of that. So if D was 0, assume D is 0, what would happen? So you would have in your X dot 1 will be only a function of X1, X dot 2 will be only a function of X2. They were not related, so you could not control, there's no crossover, you could not control that. That's what it means, right? So you want to make sure that that diagonal is not 0. If we had more than 2 states, then you have to check all the zeros where they are. The state has to appear, they have to, X dot has to be a linear combination of all the other states. If not all of them, at least one of the other. All right. So that's the meaning of controllability. Now, what is observability? So same thing, but in terms of the output, the measurement. If you can, if there is a finite time. So if you can, in your simulation time, go from initial state at time 0 to the final state within that time, and you can measure your output. You have measurement, but here we say observation history, but how do we observe? We look at the sensor measurements, right? So if we have observation history for all of our states during time t, then that system is observable. meaning that you can measure something. Now, sometimes a system is not observable. Some of the states, you have to estimate what that could be. Then use that as our observer. So all of these, the both controllability and observability, were introduced by Coleman. And then he also introduced Coleman filter. Coleman filter, it's kind of doing the same things. He makes a state for you, and then if you have other sensor, you can fuse to them, but you don't have to use the Coleman filter necessarily have the measurement of it. So if you were missing your design observer, that will estimate for you, and then you see what happens. So this is all requirement of learning Coleman filter or any control in the state space. Now let's see, can we create another matrix that we can use for observability? So if you have a system with x dot equal to ax plus bu, and here the output is important, right? Y of t is c of x of t. So we know that c is kind of going to play a role here. Your p of observability is going to be c times a, c times a squared, c times a n minus 1. Now, when you create this, if the determinant of P of observability is not 0, the system is observable. An example could be, I'm going to write the matrices for you. Let's say A is 0, 1, 0, 0, 0, 1, negative A0, negative A1, negative A2. Any values you could put there. And your C is going to be 1, 0, and 0. For this one, if we find CA would be 0, 1, 0, CA squared would be 0, 0, 1. Now, your P0 becomes 1, 0, 0, 0, 1, 0, 0, 0, 1, right? The determinant of PO is not 0. It's going to be 1, which is going to be 1, which is not 0, so is observable. So again, your system doesn't necessarily have to be like you're aiming to exactly 2 by 2. It could be anything. You just create that your controllability matrix or your observability matrix and get it determined. You put S. So all of our designs, our controller are going to be if the system is controlled. So you're going to assume I'm going to give you a system that are controllable if I ask you to design a control. Okay. If I ask you, you can just check. Now, for your class participation, I chose a system, and I want you to check if it is observable, if it is controllable. There is some time left. If you want to do it now, you can. If not, you can go home. So, well, no, you have to submit by 4. Never mind. You actually have to do it now. I'm gonna give you the password.